as has been the pattern you might have noticed with a lot of stuff in trig and inverse trig, we're going to look at the case of sine, spend some time developing that, and then you can pretty much work out cos and tan on your own steam. Okay? So let's consider this, and what I'm after is its derivative. Okay? Now, just like before we said, was it a 4-unit lesson? You know, things we know about integration we get from differentiation, right? Well, a lot of the conclusions we're drawing about inverse trig you get from regular trig, right? So how can I rephrase this in terms of regular trig so that then I can work with it? Because I know heaps of stuff about regular trig, right? Well, we've learned that if this is the inverse, right? I should be able to say that x equals sine y for certain values of y. Which ones? In what cases are these two equivalent? Because they're not always, right? We have a restriction. What kind? We have a range restriction. Do you notice why, at this point, it's kind of not very useful to us to mention the domain restriction? Anyone see why? What's the domain restriction on this? We just talked about this. It's -1 to 1, isn't it? Sorry, of this, right? But then again, this is always from -1 to 1. The whole, you know, snake that goes up and down, right? If you say x is between -1 and 1, you haven't really restricted it at all, right? This is the important part, okay? So long as I keep this in mind, which by the way is critical, right? We talked about nuances before, which we usually just sort of skirt over. You cannot afford to do that anymore. This is gonna become critical to our argument later on. In this range, we can say these two are equivalent. In that range and only that range. All right, now we want a derivative, don't we? You can differentiate this, right? What would its derivative be? It's not in terms of x, is it? It's in terms of y. So instead of dy on dx, I will get dx on dy, like so. I am differentiating with respect to y. Okay, don't get confused, they're just labels, right? I can call them whatever I like. So the derivative of sine, of course, is cos. Okay, that's good, that's progress. I have a derivative now, but I don't have the derivative that I want, right? I want dy on dx. So, this is a fraction, right? I can take the reciprocal. Movie magic. Okay, that's nice. That's good. Is that what I wanted? Kind of. I wanted dy on dx. I've got an expression for dy on dx. The only problem is it's a bit weird because it's in terms of y. It's a bit weird, isn't it? Okay. So how can I rephrase it in terms of what I know x to be? Because I want dy on dx equals blah blah blah, some function of x. Okay. Now here's the thing, right? We have this relationship already built in. This is cos and this is sine. So how can I relate cos and sine together? I could do this, but that's not going to particularly help me here because it won't get rid of my y, right? So what else could I do? What other kinds of options do I have? I could think of Pythagoras, couldn't I? I can think of Pythagoras. The Pythagorean identity here, don't forget I'm in y's, right? Tells me that sine squared y plus cos squared y is equal to 1. Happy with that? Okay. Now I want to get rid of a cos y and replace it with a sine y. I can do that. That's not that hard. Cos squared, kick the other guy over to this side. Now, what will my next line be? Take care here. What's the next line going to be? I want cos, so you would take the square root of one side. What are you going to end up with on this side? I'm at least going to get that because I've taken the square root of the left-hand side, so I better take it on the right-hand side. But I'm missing something. What am I missing? Plus or minus. I'm missing a plus or minus. Now, let's stop here for a second. I could argue this another way, okay? But I think we have enough information on the board for you to say, no, this is actually not true. Cos y is not plus or minus the square root of 1 minus sine squared. But why not? We're looking at this and we're saying, look, cos y, there are two alternatives. Two mutually exclusive alternatives for what it's equal to. Okay? Now it's equal to one of them and only one. But the question is, which one? Okay, so you're suggesting it's the positive one. Why? Now I'm happy to accept that, but you need to give me a reason. So, I did give you a big clue before, didn't I, right? I said, you noted down a range restriction, and I said it would be critical, right? So think about how this makes a difference on this, right? There are y values here, so therefore cos y can't just be anything. What does cos y look like? In this domain, sorry, this range, actually no, I am thinking of domain now, because I'm going to graph y on this axis, and I'm going to graph cos y on this axis, okay? What's it look like in that domain? Well, the whole graph looks like this. But which section of that are you interested in? Just that middle section, aren't you? Negative pi on 2 up to pi on 2. There you go. And I'm going to include those boundaries. That's okay because they're 0. No problem. Okay. So you can say this equals this because, but cos y is greater than or equal to 0 in the values of y that I'm interested in. Cos y is greater than or equal to 0 when I apply this restriction. Okay? So now you're starting to get a hang of the fact that restrictions make all the difference here, right? You can't just say it's the positive one because I want the positive one, okay? You need to provide some rationale. All right, great. I'm going to bring that over here now. 1 over the square root of 1 minus sine squared y. Okay, happy with that? And of course I know what sine y is. It's x. So I have an answer. Ta-da! That's the derivative of sine inverse. It's a little bit unusual, isn't it? You differentiate trig functions and you get trig functions back, and we're used to that. You differentiate inverse trig functions and what you get looks nothing like an inverse trig function. That's interesting. Now, I said to you before that this was not the only way to argue this, right, and get one answer at the end. Let's just have an experiment. Suppose I did not draw this conclusion. I got to here and I was like, oh, no, okay, let's just see what happens, okay? How would that change what happens on the left-hand side? If I carry this plus or minus with me, I would get to here, and then I would get to here. And then I would scratch my head, right? We're not used to differentiating things and getting out two derivatives, because that's two derivatives, isn't it, right? Why am I getting two derivatives? Like, did I do something wrong? For what reason would I get two derivatives? Now think about this. The reason I would get two derivatives is because I have not accounted for this restriction, right? It was accounting for the restriction that limited me to one of the two. Does that make sense? Okay. Now tell me, what does this thing look like without restrictions? I think it looks like this. Let's see. Increasing. Okay, so there's the middle part. And then the rest of it, having not restricted it, looks like this. Okay, now look at it. With the restriction, which part are we interested in? We're interested in from here to here. What can you tell me about the gradient, the derivative, in that section? It's, well, it's always positive except for, where's it not positive? At the endpoints, right? At the endpoints. The derivative is not positive because the derivative doesn't exist there, right? Because when you stick in -1 or 1, what happens? You divide by 0. Of course you do, because you've got a vertical. Okay, you get it, right? So therefore, in this little section, it's always positive. But if you don't restrict, if for instance you're looking up here, that's not positive. That's negative. And it's exactly the negative, like it's plus or minus, it's the negative of what you would have if you looked at one of these areas. You see they're exactly opposite to each other, right? So that's why you differentiate something, it looks simple. Why do we get two derivatives out? Because you have language for this. This sucker is a relation. Of course he has two derivatives. Maybe if it was a really weirdo looking relation, we'd get more, right? But it just so happens that you've only got two possible things you could be. You could have the increasing version or the decreasing version, depending on where you are. That make sense?